I'm presenting a scenario about interpreting a partial dependence plot, a visualization tool in Sklearn, a popular machine learning library in Python. We're looking at how two features, feature_A and feature_B, relate to a target variable using a gradient boosting model. The plot will show us how changes in feature_A and feature_B affect the prediction. This statement is incorrect. A partial dependence plot shows the average effect of a single feature on the target variable. It doesn't directly show how feature_A and feature_B interact. This statement is true. A positive relationship means as feature_A increases, the predicted target value tends to increase, assuming all other features remain the same. That's the key idea of a partial dependence plot. This is also true. A non-monotonic relationship, think of a curve with ups and downs, means the relationship between feature_B and the target isn't simply a straight line. A linear model would struggle to capture this type of complex relationship. This is correct. The plot shows the average effect of each feature, ignoring potential interactions between features. It's an average effect, not the complete picture. It simplifies things to make interpretation easier, but this simplification could miss some nuances. This sets the stage. I'm describing a situation using a specific visualization tool from Sklearn to analyze the relationship between a target variable, what we are trying to predict, and two features, variables that may influence the target variable. We have results showing different relationships for those features. This refers to the variable we're trying to predict using the model. Think of it as the outcome we want to understand. In this case, we're using a gradient boosting model to predict this target variable based on the values of features A and B. I see a clear positive trend. As feature A increases, the target variable also increases. The partial dependence plot shows this directly. This implies that a higher feature A value is associated with a higher predicted target value, assuming other factors stay the same. Here's where it gets interesting. The relationship between feature B and the target isn't simple. It's not consistently increasing or decreasing. I see peaks and valleys in the partial dependence plot, which indicates a complex nonlinear relationship. This suggests a simple linear model might be a poor fit. The partial dependence plot does not show interaction effects between features A and B directly. It only shows how each feature individually affects the target, assuming other features are held constant at their average values. I agree. The curved, non-monotonic relationship for feature B strongly suggests that a linear model, which assumes a straight line relationship, would not accurately capture the data's complexity. A more flexible, nonlinear model would be a better choice. Precisely. The partial dependence plot focuses only on the average effect of each feature on the target, ignoring how different feature values might interact to affect the prediction. This averaging process means it might miss subtle, complex interaction effects. This question tests your understanding of how to interpret the information given in a partial dependence plot, created using Sklearn's partial dependence display. Specifically, we are looking at how to interpret the relationships displayed for two features, feature A and feature B, in relation to the target variable. This refers to the visualization tool used to display the relationship between features and the target variable from the model. A positive relationship on a partial dependence plot means that increasing the value of the feature is associated with an increase in the predicted value of the target variable. This assumes all other features remain constant. This describes the overall task: correctly interpreting what a partial dependence display shows about the relationships between features, independent variables, and the target, dependent variable. What you are predicting: upward trend, curved, nonlinear trend. No, it does not. Correct. Correct. Main question of this quiz. Visualization tool. Correct. Quiz objective. This question tests your understanding of how to interpret partial dependence plots created by Sklearn's PartialDependenceDisplay. I'll explain what partial dependence plots show, and what they don't show, so you can answer the multiple choice questions correctly. Let's dive in. If the partial dependence plot shows a positive relationship between feature A and the target variable, It means that as the value of feature A increases, you tend to see an increase in the predicted value of your target variable. Importantly, this is true while keeping the values of all other features in the model fixed at their average values. A non-monotonic relationship means the relationship between the feature and the target isn't simply going up or down. It could go up, then down, then up again. This curve shows a nonlinear relationship which a simple linear model won't capture well. Think of it like this: a straight line can't fit a curvy road. The partial dependence plot shows the average effect of each feature, ignoring how features might interact. It's like taking a snapshot of the average effect while smoothing out any details of complex interactions between features. It simplifies the picture, but may miss some subtle details. I'm interpreting a plot created using Sklearn's partial dependence display. This plot helps me understand how a single feature impacts the prediction, while keeping other features constant at their average values. It's like taking a snapshot of the feature's influence in isolation. The quiz asks me to interpret a partial dependence plot from a gradient boosting model, focusing on how feature _A and feature _B affect the target variable. I need to identify correct interpretations of the results, understanding what this type of plot can and cannot tell me. The scenario sets up the core problem. I have a partial dependence plot, created using Sklearn's partial dependence display, for a gradient boosting model. The plot displays how feature _A and feature _B individually affect my target variable. Feature _A shows a clear positive relationship. However, feature _B exhibits a more complex and wavy, non-monotonic relationship, indicating changes in direction. The question tests my ability to correctly interpret what this means. Partial dependence display is an abbreviation for partial dependence display. If I see a positive relationship between feature _A and the target variable on the plot, it means that as the values of feature _A increase, the predicted values of my target also tend to increase. Importantly, this holds true while keeping the other features constant at their average. This is a direct interpretation. A non-monotonic relationship means the relationship between feature _B and the target isn't a straight line. It goes up and down. This suggests a linear model, which assumes a straight line relationship, would be a poor fit for this data because it can't capture those curves and changes of direction. A nonlinear model would be more appropriate. The partial dependence display shows me the average effect of each feature, averaged across all possible combinations of other features. It does not show how features work together, interactions. This is a key limitation. I need to remember that these plots are showing me average marginal effects of features and not capturing higher order or complex interactions between variables. A partial dependence plot displays the marginal effect of a feature on the target variable by averaging the effect across all other features. It's a really useful way to visualize and understand how individual features contribute to predictions. It's a key tool for understanding model behavior. I'm explaining how to interpret the results from a partial dependence display, a visual tool used to understand how individual features influence predictions in a machine learning model. It's like looking at a zoomed-in view of each feature's influence on the outcome, one feature at a time. We're going to analyze a partial dependence plot, a visual that shows how changes in a feature affect the prediction, from a gradient boosting model in Sklearn. This specific plot is showing how feature _A and feature _B relate to the prediction. We'll determine which interpretations are correct. Let's dive in. This describes the setup of the problem. We have a plot showing how two features affect our model's predictions. Feature _A has a simple positive relationship, meaning as it increases, the prediction increases. Feature _B, however, shows a more complicated, nonlinear relationship. The key is to carefully interpret this relationship and identify correct statements about the plot. This statement is incorrect. Partial dependence plots don't show the direct interaction between features. They focus on the average effect of each feature individually, ignoring interactions. It's like looking at each player's individual performance separately, rather than their teamwork. This statement is correct. A positive relationship directly means that as feature _A increases, the prediction increases, assuming all other features remain unchanged. This is also correct. A non-monotonic relationship, up and down curve, suggests a nonlinear relationship. A simple straight line won't capture that pattern. Therefore, a nonlinear model is more appropriate. This statement is true. Partial dependence plots average the effects across all other features. They simplify things, so they may miss complex interactions between features. It's like taking the average score of a basketball team. It tells you something, but misses the individual brilliance of each player and how they interact on the court. This summarizes that we need to understand what the partial dependence plot is telling us about the model's behavior and the relationship between features and predictions. We assess if the model correctly captures the feature importance. I interpret this as understanding how to read and use information from a partial dependence display, PDP. A PDP visualizes how a single feature affects predictions, averaging across other features. It's a valuable tool for understanding the relationship between features and the target variable in your model. This means a PDP shows the average change in prediction as you change a single feature. I will ignore how other features might interact. Think of it like this. I'm looking at how much your exam score changes when you study more hours, on average, regardless of whether you're tired or well rested. The PDP gives me the average impact of each feature. It's not showing interactions where two or more features work together. For example, maybe studying more hours helps, but only if you are well rested. A PDP averages that, so it might miss the real impact of the combined effect. The question tests my understanding of how to read a PDP created using Sklearn's partial dependence display. I need to know what the display shows and what it doesn't show and correctly interpret different relationship types. This statement is true. A PDP only looks at the average effect of a feature. It simplifies things by ignoring complex interactions between features. For example, I can see how exercise affects weight loss on average, but the PDP ignores the fact that diet also plays a role. So, it doesn't show the whole picture of how exercise and diet together influence weight loss. This is correct. A non-monotonic relationship means the relationship isn't a straight line, it goes up and down. A linear model assumes a straight line relationship. So if I see a curvy line, a linear model is unlikely to capture the relationship accurately. That's right. A positive relationship on a PDP means that increasing the feature generally increases the prediction. For example, if I see that more study time generally leads to higher exam scores, this is indicated by the plot showing a positive trend. I am holding other things constant, meaning I'm not considering the effects of other things like how much sleep you get. I interpret this as understanding how to read and use a partial dependence display, PDP, to understand the relationship between features and a target variable in a machine learning model. A PDP shows the average effect of a single feature on the target variable, holding other features constant at their average values. It's a great visual tool, but it has limitations. This is the core question of the quiz. You're asked to interpret what a PDP from Sklearn, a popular Python machine learning library, is showing about the relationship between two features, feature_A, feature_B, and the target variable in a gradient boosting model. This statement is true. A positive relationship in a PDP simply means that as feature_A increases, the predicted target variable also tends to increase. Importantly, other features are kept constant, as in, held at their average values. This is also true. A non-monotonic relationship, a relationship that's not simply increasing or decreasing, indicates that a linear model, which assumes a straight line relationship, would poorly capture the relationship between feature_B and the target variable. A more complex model would be needed. This is correct. The PDP shows the average effect of each feature. It doesn't show how the features interact with each other. For example, it doesn't show if the effect of feature_A on the target changes depending on the value of feature_B. That's why we need other plotting techniques to show such interactions. This is false. The PDP is not designed to show interactions between features. It shows how each feature affects the target variable individually, holding other features constant. To look at interaction effects, you need different analysis techniques. This refers to the type of plot generated by the partial dependence display function. It provides a visual representation of the relationship between features and the target variable. This describes the relationship observed in the PDP for feature_A. There is a positive association. As feature_A increases, the predicted target increases. This indicates the type of relationship observed in the PDP for feature_B. It is not simply going up or down, it has peaks and valleys, hence the non-monotonic descriptor. This is what you're trying to predict with your machine learning model. It's what you're examining the relationship with feature_A and feature_B.